Welcome everyone. Today we have Emilia that speaks for the AJS seminar. So Emilia is a PhD candidate at the University of Tubingen under the supervision of Prof. Philip Henning. She's also part of the AJS program, so she spent part of her PhD in Genoa with a group of Lorenzo Rosasco. And today she will talk about learning solution operator for PDEs with some uncertainty quantification. So please, Emilia, the floor is yours.
Thank you very much for the introduction. Sorry for the delay. Okay, I will then start right away. So today we're going to talk about learning solution operators for PDEs with uncertainty quantifications. So a little bit of motivation. So PDEs are our language to describe the interactions or the complex interactions that arise in many different dynamical systems. For example, real-world phenomena such as predicting the weather changes or some extreme weather events. Here you can see in the slide the ERA 5 dataset of the wind speed around the Earth. So in the last decades or last years, I would say that there has been a shift from numerical simulations of PDEs, so numerical weather prediction. So these are classical numerical methods to solve PDEs, to data-driven methods. And these are neural networks, usually deep neural networks, that are aimed to capture the relationship between input and outputs. And data-driven methods are, some of them are black box, so they don't have any knowledge of the PDE, but they have become quite popular in the last years because once trained, there are several orders of magnitude faster as compared to classical numerical methods. So one of these are, for example, ForecastNet. That is the one that you can see in the picture. This is a prediction of the ERA 5 dataset of the previous picture, and this uses Fourier neural operators. And these neural operators are one of these data-driven methods that I will focus about today. But first, a little observation. So if you see, or a further motivation of this talk is that even though these methods have become very popular and have shown to be quite good to solve or to learn the dynamical systems or the PDEs that describe the dynamical systems, if you look at the predictions, often you notice that there are areas with errors that can be, at first sight, difficult to be spotted by a human eye. And this can be due for several reasons. One of these, for example, is that the data is captured. It's difficult to collect the training data, and it's usually on a lower data resolution than the one that you would like to have for the prediction. Moreover, you can see that sometimes in the prediction, which is in the picture above compared to the truth, you see a smoothing effect of the prediction. This is sometimes due to the fact that when you train, you use a mean square error loss that smoothens out the prediction. So this plot screams for uncertainty estimates, and this is actually the topic of my talk today. So what I'm going to talk about is not, or my goal here is not to motivate why neural operators, which is the main architecture I'm going to talk about today, are the ones that you should be using. What I want actually to claim is that if you use them, you should be able to quantify the uncertainty. If you are wrong, these methods should be able to know that they are wrong. A little parenthesis that I come from the School of Probabilistic Numerics, or at least the group I am doing my PhD with, Philip Henning, and this is a school that aims to quantify uncertainty that arise from intractable or incomplete numerical computations and treats numerical problems as one of statistical inference instead. So what classical numerical methods do, they output point estimates, whereas probabilistic numerics aims to output entire probability distributions over the output. And this comes with a lot of benefits, which, for example, is encoding structural knowledge about the problem, for example, through a prior distribution. This is in the Bayesian view. So there are many different applications, linear algebra, quadrature optimization, and you can check out the link if you're interested in the topic. Okay, let's dive. Please interrupt me for any question. I will try to go a little bit faster, but you're very welcome to interrupt me. So we will start by a brief introduction about how neural operators learn partial differential equations with ease, and then we will try to answer two questions. The first one is if we can provide Fourier neural operators, so a particular type of neural operators, which are the most used one, which are the Fourier neural operators with uncertainty estimates. And the quick question is yes, we can using Laplace approximation. And then we will proceed by observing that neural operators are actually operators, as the name suggests, that map between function spaces. And function spaces are infinite dimensional function spaces, so they are a bit more complex objects to think about. So we want to generalize the first question and ask ourselves if what does it even mean to put a belief over operators, over a map between function spaces. We will do this in the framework of Gaussian processes. And the bit to memorize is that linearization turns neural operators into function valued Gaussian processes. This means that through the framework of Gaussian processes, we will actually try to define what it means to put a belief over a neural operator. Maybe a little observation. So the first question is basically a paper that we submitted to an ICLR workshop this year. And it's kind of an introduction to question number 2. So it kind of prepared the grounds of for the generalization, which is question number 2. So it's a bit more a naive approach for what is actually more recent work that has been uploaded to the archive recently, and will be question number 2. But let's start with a brief introduction. So how can we learn to solve a PDE, a parametric PDE? So if we assume that we have a differential operator, L, depending on a parameter A, that's why we call them parametric PDEs. And A in general, now the precise nature of this space is not of interest for now, but you can think about it as a function space or a Banach space or what you want. So a PDE in its more general form is written in this formula here that you read in the screen, where you have the differential operator that is applied to a function u and the right-hand side function f on a domain D, let's say of a subset of Rd, and then you have a boundary condition on the boundaries of D. So what classical solvers do, so if A is fixed, they discretize in space, and then they use numerical methods such as finite element methods or finite differences. I'm sure you've heard of this. But what you can do is you can think at this problem at a level of abstraction above and think at the map that maps A to the solution for the corresponding A. So this means that you make A vary and take it as an input of a solution operator. So for every new A that I give you, you will have the solution corresponding to that A. A in this case is the parameter of the differential operator, but in general, it can be, you can think of it as F, so the right-hand side function, even the boundary condition or the initial state. And this is somehow not only a more complex problem because this F maps between two function spaces, but it's also, so ideally, if you would be able to learn this operator, you've learned a family of PDEs for every new A. So I can give you a new function, and you can have the solution for that A. So it's a level of abstraction or generalization above the problem. And in fact, neural operators are exactly tailored to learn this type of operators, and they are formally defined as maps from Banach space of functions A and U and a set of parameters that we will call W, that is a subset of RP. And what they do is that they iteratively learn the solution by starting with the projection on a higher dimensional space, and then iteratively through different layers that we will see which forms these layers have, then they update they update at every layer, iteratively learn the solution that will be then mapped back through a back projection in the space and have you. One of these architectures is, you probably have heard of it, are Fourier neural operators. And there the layer have the form that you see in the picture that I will comment now in a moment. Maybe in a nutshell, we can say that neural operator architecture will apply all the spatially global operation in the spectral domain. In fact, this is what they do. You can see that, okay, since at every layer, they will have the so-called Fourier layers. The idea is that usually, so in neural operators in general, these are layers that have an integral form. In this case, these are convolutional layers. But since convolution in spatial domain is equivalent to pointwise multiplication in Fourier domain, what they do is they do a Fourier transform, and then they apply a linear transformation in frequency space, and then they go back into, with an inverse Fourier transform, they go back into function space. And this is what this part of the network does, where I omitted to say that when they do the Fourier transform, they also truncate the higher frequencies. So they apply the linear transform only on the lower frequencies, but at the same, this is also for computational reasons quite handy, because Fourier transforms can be can be computed very fast in a computer with fast Fourier transform if you have an evenly spaced grid, which is the case for Fourier operators, or at least how they apply it. But at the same time, to recover the information that you get lost in spectral domain by this cutting discrepancy, they also keep a linear transformation W in spatial domain. And then they add it up. So this is what happens at every layer. Just to add a little bit of notation, I omitted that at the beginning, P and Q are just some lifting and some projection that operate pointways in the spatial domain. So you're just lifting it up to a higher dimensional space, and then you project it back. And the set of parameters here, sorry, this shouldn't be RD. This should be a higher dimensional space. And the W is just the set of parameters that consist of the parameters of the projection at the beginning and the parameter of the lifting and the projection, and then W1, R1, and there are parameters for every layer until L-1. So let's assume that we have L layers. A couple of comments of these Fourier operators. They are very fast, so they have been shown to outperform many existing deep neural models. And there are also there are some theoretical results regarding them, in the same way as neural networks have been shown to be able to approximate any continuous function. There are results that you can see in the reference, that you can check up in the reference that I put as a subtitle, that they are able to approximate any continuous operator on a compact set of a Banach space. As I mentioned before, they have been used in many useful applications. One is, for example, climate. This is the wind speed on the Earth. They have been used also for plasma modeling, but also for 3D turbulence. And you can check out many of the useful applications. One last comment, they are known to be discretization invariant, and this is a bit of actually also the core of what I will talk about later. The idea is that you can, what does it mean? Is that you can train on a grid and then evaluate on a different grid. So you can generalize to a different mesh without the need of retraining the network. And this is a desirable property for mappings between function spaces, because ideally, if you want to output a function, you would like to be able to evaluate it at any grid you want. In practice, when FNOs are trained, they are discretized on a grid during training. I will maybe comment on this on a later point, but they are known to be discretization invariant. Okay, how can we provide FNOs with uncertainty estimates? So as I said, so now we have these deep architectures, and we would like to have an uncertainty estimate over the output of this neural network, and we will do this through Laplace approximation. I here refer to ensemble predictions because for this first question, we submitted to also a workshop that also was in the community of weather forecasting and people in climate models that usually use ensemble predictions for applying for seeing uncertainty over the output. So they produce different ensembles predictions and then compared to be able to have a range of possibilities over the output. Okay, the idea is old but gold. It dates back to Laplace. I will just briefly give you a visual idea of what the Laplace approximation is. So imagine that you have a distribution in black, and you would like, so the black line in the plot, and you would like to have a Gaussian approximation of this distribution. So what you visually would like to do is you would like to fit a bell that approximates this distribution. So what do? You find the mode, which is this point. I hope you can see my mouse, the mode of this distribution. And then to fit a Gaussian bell, you want to know how much you want to curve the bell, or how much the curvature should be. So in terms of the distribution, is the variance of the Gaussian distribution. And the geometry tells us that the curvature of the bell is given by the second derivative. So you basically need two things for this approximation. First is finding the mode, and second is the second derivative at the mode to find how much the bell should be curved. And this is exactly what happens in the Laplace approximation. So if you do a Taylor expansion of the distribution, a second order Taylor expansion around the mode, you can see that since the first derivative at the mode is 0 because it's a maximum, you end up with something that has exactly the form of a log PDF of a normal distribution, where the mean is the mode and the variance is the inverse second derivative. And this is exactly what the Laplace approximation is. So the two objects that you need is going to be the mode of the distribution W hat and sigma square, which is minus the second derivative at the mode. Okay, how do we apply this to neural networks? Since if the idea is quite old, it has been applied to deep learning at the end of last century, and is now very popular in deep learning. So it has been used a lot in the last year. So imagine that you have a neural network F from RD with P numbers of parameters to R capital D, and a set of data, UI, VI. In this case, I changed a bit the notation. I used UI, VI instead of the classical X, Y, because here you can think of function spaces. So these are discretized functions. So during training, classical training of neural networks minimizes an objective function, which is the sum of the empirical risk and a regularizer, which in a Bayesian view are nothing else than the log likelihood and the log prior. I think you're familiar with this Bayesian view of this objective function. This means that, so for example, a common choice for the prior is a Gaussian prior, and this corresponds to a L2 regularizer over the parameters, and so a Gaussian prior over the parameters corresponds to a L2 regularizer. So what you do during training, you try to find the minimum of this log posterior. So in the same way as I explained before, so by doing, sorry, is there a question? No. In the same way, by doing a second order Taylor approximation, yields a posterior distribution of the weights given the data. That would be a normal distribution, so a Gaussian distribution of at omega star, which is the minimum that you would find usually during training, and the negative inverse Hessian of the log posterior. And the point is that here, so the Gaussian distribution at the mode, this omega star is what you find anyways during training. So the only computational overhead that you have for doing Laplace is being able to compute this inverse Hessian, which admittedly can be expensive if you have a lot of parameters, and there are various techniques to make this tractable, and we will see this in a moment. A little spoiler here. So in point 2, we will actually see that we will do a further approximation, because this is only the posterior distribution of over the weights given the data. We're actually interested in a predictive distribution over the output of the neural network. And this, if we do a further first order approximation and linearize the network, since Gaussian distribution behave well with linear maps, we will have also distribution over the output of the network. But this is just a little spoiler of keeping in mind for what we will do later. Okay, how do we apply the Laplace approximation to the Fourier neural operator? So for scalability, we will apply it only on a subnetwork, in this case on the last layer. This is also something very common that is done with Laplace approximation over neural networks. And which layer do we choose? We treat only the last Fourier layer probabilistically. Last Fourier layer, I mean the last layer only on R, so the parameters that are connected to the Fourier transform. There are some motivations why we decided to use this last layer. I mean, Q is applied only pointwise and does not capture any global structure. So also empirically, we showed that with R, it was a good choice between scalability, but also trying to capture some uncertainty. There are some also another little caveat, which is R in general are complex parameters, because we go into Fourier space, and when you map into Fourier space, the frequency space, you can have complex number, but this is not a problem because it just isomorph to R2 by considering the real and the imaginary part. Two last observations: since the Hessian can be quite expensive to compute, we will do two approximations. One is the GGN approximation. It is a positive definite approximation of the Hessian, which is very used in deep learning. Since in general, the Hessian might not be positive definite, you just decompose it with the GGN. And we use a K-FAC approximation. K-FAC approximation is just a block diagonal approximation to enable an efficient storage and computation of the inverse to make it trackable. We can go into the details if you have further questions. It's just a way to compute the Hessian of the Laplace, so the covariance matrix. So what do? We sample from this Laplace approximation, and then we pass an input to get the corresponding ensemble predictions for every sample from the Laplace. you can see some application to the Korteweg-de Vries equations compared to classical methods that are used, or usual methods that are using in ensemble predictions for climate. Here in red, it is our method. What you can see is that not only compared to the FNO perturbed, which is just perturbing the input, this is something quite common, to perturb the input and see the corresponding output, or by the FNO ensemble, which is training directly on a set of prediction on a standard loss function. We can see that our method not only seems, at least in the short run, has a clear better uncertainty quantification by having a better standard deviation that captures how wrong the model is, but also the samples seem to be more reasonably behave reasonably compared to the other two, where the first one is very rough and non-continuous or non-smooth, sorry, and the second one doesn't capture at all the uncertainty. And with first and second one, I was referring to the rows of this plot. And this can also be quantified on a table. So we try to compute some measures to quantify the uncertainty that are usually used. So randomized mean squared error, or what we call a Q, which is a posterior calibration that should be close to 1, and a negative log likelihood. You can see that at least in a short training run, our method seems to be better than their alternatives. On the long run, also there are some cases where it's better, but it was not that clear as for the short training run. Okay, I'm trying to go a little bit faster, but as I said, please feel free to interrupt me at any moment. So this was actually the prepare the ground to the next question. So what we see now, okay, we wanted to add some uncertainty quantification to the Fourier neural operator, and we did a Laplace approximation over the parameters of the network. And this induced some ensemble predictions over the output. But now I stop for a moment and I say, okay, but I defined these neural operators as some operators, indeed, some mappings between infinite dimensional spaces. So what does it even mean to have a distribution over an operator? So can we put a belief, and for us it would be a Gaussian belief because we would do it through the framework of Gaussian processes, over an operator? And for that, I will use the language of Gaussian processes. I don't know if you're familiar with Gaussian processes, so I will do a little recap, because what we're going to do now is defining what it is a function valued Gaussian process. And this is an object that can be a bit vague, or a bit not very vivid to understand what it means to have a Gaussian process that has values in a function space. But I hope to arrive now in a gradual way so that maybe you understand where I want to go to. So what in the scalar case, so imagine you have a function that goes to R. This is a classical function where A, we call it an index set. It's an input. If you think for now that it's R, it's as you prefer. What we're interested in now is that it's scalar. It goes into R. So what a Gaussian process is usually defined on an index set A, with an index set A and a probability space omega and a sigma algebra and a probability measure. It's a function such that every time you fix endpoints, these points are Gaussianly distributed. So this is a multivariate Gaussian. So really, when you think at a GP, a Gaussian process, what you do is think, okay, every time I fix endpoints, the object, the set of FA1 omega FIN omega, since it's a random variable, because omega is the set of possible events. So this F is a stochastic process. But what I'm interested in a Gaussian process is every time I fix endpoints, the resulting Rn valued random variable is Gaussian. You might have heard of Gaussian processes as probability measures over functions. And the idea that justifies this interpretation is that you can redefine this, or think at this F as a map from omega, so the space of possible events, to a space of functions. So if I see the map from omega to F, which is a function from A to R, with the necessary Borel product sigma algebra. But what I just want to highlight here, that this is why often GPs are thought as probability measures over functions. So you've probably often, if you did, or I don't know, you saw this plots, which are basically you have a prior distribution over what possible function could look like, the function I want to infer. And then when I collect data, I update my belief, and I end up with a posterior distribution. So in red, you can see the posterior mean. In light red, you can see the samples from this posterior distribution, and in gray, the standard deviation from the mean, and in black, the points I collect. Okay, now what happens if we move from R here to RD, a multi-output GP? Really, the step is really, really little. What is a multi-output Gaussian process is really basically the same. It's just that now my output space is RD. So every time I have F evaluated at this n number of points that I'm interested that are multivariate Gaussian, I just have a dimension more. I have that this F's A1 and FAN are vectors, but I don't really care about this because I know how to stack vectors. And the idea is that in RD, stacking vectors and considering the corresponding product sigma algebra is the same as the product topology is the same as stacking the topologies of R. So really, the definition stays the same. It's just that now I will just stack the vectors and say that these are R n times d evaluated Gaussian random variable. There is an observation that is crucial now that I want to make, is that I can relate multi-output GPs to scalar GPs by just augmenting their input space. And this is also usually what you do when you work in code. So if I define F that goes from A omega to RD, this is a multi-output GP, so a D output GP, I can just augment the input space. And with augment, I just take in the input space I, which is the index set 1 to D. We can also see it in this equation here. So it's I'm just saying that F evaluated at A and take the eth element or the ith element in the output space, it's the same as Fi for the specific A, for that specific A. And you can see that here, I'm just rephrasing the multi-output GP as a scalar GP, just by putting the dimension D into the input space. And this will be useful in a moment, because now I'm just doing the further step. That is maybe the more difficult to think about what it means to have as an output space a function space. So now from RD, we go as an output space, we have a Banach space of functions in general from a domain DU to RD. Okay, now the definition actually stays pretty much the same. So we have, I say that a U-valued Gaussian process is with the index x A is a function which goes now from A to U, and A times, of course, the probability space, where once, if I evaluate it on endpoints, this set of endpoints, so this FA1, FAN, are UN valued Gaussian processes. So they are Gaussian random variables, sorry. Now, I don't want to stop and talk much about what does it mean to be a function valued Gaussian random variable. So what does it even mean? What I want to stress out here is that I can do the same trick as before and reformulate this function. So the function big F that goes from, that is the one that maps between two Banach space of functions, by augmenting the input space and take the domain of U into the input space. And now this is a multi-output Gaussian process. So, because the point is, how do we stack functions? Well, as before, I can just relate it to a multi-output GP. And what you can see is really they relate one to each other, but when the first one applied at an A and then as a function of the second variable and then evaluated at X is the same as this F, which is a multi-output GP, at fixing A, X, and then evaluating at an event. And this duality is what we want to use in this reasoning, because on the left-hand side is what you theoretically would like to have. So what you think about is, okay, I want a function value GP, like I want a Gaussian belief over objects that map between infinite dimensional spaces, between Banach spaces of functions. And on the right, we just rephrase it in a way of something that we can put on a machine, that we can compute, because we know how to compute GPs on a computer or on a machine. And so if we think what is on the left, we actually then do what is on the right, but they're really equivalent. And you can check also on the paper that we also prove how these two objects are equivalent also in terms of the mean and the covariance. This also relates what I just did. So this bridging, or this duality between a function value GP and a multi-output GP, relates to the concept of currying in functional programming. I don't know if you're familiar with it. The idea is that if you have a function that goes from a product space x, y to z, currying reformulates this function as a sequence of functions of a single argument. That means that I just reformulate as a function g that goes from x to y to z. So it goes to a function space indeed. The idea is that you might not have all the variables at the same time that you need to compute f. So what you do is that you just take them during the computation when you actually have them, so that you apply them recursively when you need them. And what you end up, so the computation is the same. So g of x and then apply to y is the same as f of xy, but this is just rephrased different in a way that I first apply x, and this is a function, g of x, and this function now applied to y. And this is what we did before. It's just we did this Gaussian currying of having a random function of this form and rephrasing as a Gaussian random operator that goes into a space, so A, and then it goes into a function space with domain U. And really, the duality is written here. I hope it's clear what I'm trying to say. I'm happy to answer any questions. And this is really, okay, this is the first bit that we need for our method to put a Gaussian belief over neural operators. The second one is what I said basically before. We just do a Laplace approximation of the parameters, and then we linearize the network to get a distribution over the output of the neural network. Here I phrase it a little bit different just to motivate why we use the GGN approximation over the Hessian. So if you have a neural network as before and you have an objective function, this is what you want to minimize during training. This is the one that you saw before. I just call it R. What I do, I just now do it in a little different order. It's just that I linearize the network with a first order Taylor approximation around the map estimate, so omega star. I would call it F linear omega star in X and Y, and I linearize it around omega star, and this is just the gradient of F at omega star. And then I do a second order Taylor approximation of the linearized model. And this is just really what you saw before with the second order Taylor expansion. It's just that now the matrix, so the tensor, the covariance matrix, in computation, you can see that this is actually the GGN. So it's just the way to make the GGN arise as a natural thing to do when you want. It's not only an approximation of the Hessian, but it turns out that if you use a linearized model with of the network, so if you see the GGN as a Taylor to the model and not to approximation of the weights, it just arises in a natural way. But really what it is it's what I said before. I just do a Laplace approximation on the weights, and then I plus linearization of the network. And so I end up with a Gaussian distribution, or a GP, over F given the data. And F is now my linearized neural network. And I will have a Gaussian distribution over, or a Gaussian process actually, over with F of at omega star, and then a covariance function that is defined like this, where the options that I need are this matrix that before now I call P. It was sigma before because it was over the weights. Now P is also on the linearized network, and I have two other objects, which is the gradient with respect to the weights of F. Sorry, this should be bold. Okay, so this is the method that I tried to explain with these two different main chunks, which is a little bit of understanding what a function value Gaussian process is, and now can we apply it through linearized Laplace over the network. We called it Nola, which is neural operator Laplace. You can check out the paper that is on the archive. So the step 0 is starting from a neural operator. We have a neural operator that is already given or defined as the original authors do from two sets A and U, which are Banach spaces, and a set of parameters. Through currying, we can redefine the neural operator, and so that it goes to a multi-output, so that this is a multi-output GP, so it goes to RDU. Then we apply linearized Laplace. So what it means is that we assume that we have a Gaussian belief over the network, over the parameters of the network. In this case, it's a plus, but again, it can be actually any way to put in a Gaussian distribution over the networks. It can be variational inference. In this case, we use Laplace, but it's just something that I can add once I have a distribution over the parameters. Then by dual linearization around mu, which is the mean of this distribution, I get an induced approximate multi-output GP belief over the set. So with the set A times the domain of U, which is what I tried to explain before. So we end up with this. And then we do carrying again to construct the Gaussian random operator from this linearized F. So the two carrying is just when I jump from multi-output GP to function value GP are these two steps, step 1 and 3, and the linearized Laplace is step 2. You can see it visually in this picture. So if I start with a neural operator here, where I have two spaces, A and U, of functions, and a set of parameters, where here it's just this arrow is just like a delta Dirac function. They're just deterministic. With currying, I just separate I augment the input space by adding this domain of U, and this just gets the formulation that I wrote before. And the linearized Laplace approximation enters in this step, where now instead of these points, I have a distribution over W. So also on the output of the Gaussian of this neural network, I will have a distribution over the output that is now RDU. And then I do again Gaussian currying so that, or not again, I do the Gaussian currying so that I actually have a distribution of function valued output. Okay, and this was, so the theory behind it in a general way, having a general neural operator. We noticed that applying this to Fourier neural operator yields actually a very efficient representation of a function valued posterior process. Why? Because you can view, so this is in the second slide. In the next slide, I will become a little bit more technical, but in this slide, it's just the idea behind it. So here we have an input function, and then the Fourier transform, and then the inverse Fourier transform. So if you see only the above this yellow square, and I don't care for now for this W, what I then think of is I then think at everything before the last layer as this H function. So I go from a function space to Rn. This is the last layer before applying the inverse Fourier. So assume that I have a distribution over this last layer, then I can view the inverse Fourier as a mapping back into function space. That means that really this f to the -1 is just a multiplication with features, where Ri are the weights. So this is really a parametric GPs where I have a distribution, a Gaussian distribution over the weights, and then through the features I do a mapping back into function space. And this is really what a GP is, a parametric GP is indeed. And this is in a function space treatment, I actually end up with an object that is really a function valued thing that I can then evaluate it on any grid that I want. In fact, in a bit more technical, if I do it Fourier neural operators and FNO, I can view it as a map. This is Q. This is the back projection that I called capital Q before, and the nonlinearity applied to the last layer of XWL -1. I can decompose this as the part of the inverse Fourier transform, where this V hat is the Fourier transform V, and W, so the part that I do in space, not in frequency domain, but the transformation I add with this part, W. And this inverse Fourier is really just, as I wrote down here, a multiplication with features. Since we want to work we don't want to work with complex number, we decompose this as the real part and the imaginary part. So it's just cosine and sine features, and the features that come from the interpolation. So this W, J, and 1x is just the features. You can think as it as an interpolation of the points of that interpolates V, for example, as spline interpolation, or it can be a Fourier interpolation, but this is just the features that correspond to W. So if you have a Gaussian belief over this set of parameters, which is the real part, what I called before W, so I will just use it on the last layer, on the last Fourier layer, which are the parameters R and W. So there is this W compared to the first approach that I showed in point number 1. We also have the included W in the uncertainty quantification. So assume that you have a Gaussian belief. As I said, here it's Laplace, but it can be anything. So I can also give me this Gaussian belief over the weights, and then I can tell you how to introduce to get an uncertainty estimate over the output of the network. So I construct my multi-output GP, which is the sum of 3 parametric GPs with these 3 features. And I end up with a function value GP that induced by the linearized Fourier neural operator over the output, where Q is this map here, is the composition of the the projection and the nonlinearity, and then I would need the gradient of Q at M of X. Why is this useful? Well, the benefits is that we can evaluate the GP belief at any point X. So it's truly function valued without the need to compute more than one forward part of the neural operator, because f of A only needs access to the last state. And then in contrast to general non-parametric GPs, we can do efficient sampling of entire functions, because what happens in general non-parametric GPs, usually you discretize before, so before drawing the samples, whereas here you really just can do, since it's a parametric GPs with features, you can do an efficient way of sampling. And of course, it's a GP, so it's very cool because it's an entire posterior distribution of the output of the network. Here you can see again the experiment over the KdV equations, where we compared it again over the input perturbations and the weight perturbations, so two other way of measuring the uncertainty. And our Nola is the first plot that shows, at least quantitatively, that it seems to do the right thing. But we also tried on other types of PDEs, for example, the Kuramoto-Subashinsky or the Burger's equation. And you can see that actually our method seems to be better in quantifying the uncertainty with various types of measuring it, ways of measuring it, which is again the negative log likelihood, which reflects a balance between the low standard deviation error terms, the RMSE, so the mean square error, and the Q that I mentioned before. Yeah, we could spend a little bit of time commenting this results, but what I want to highlight here is just really that Nola, which is the last line of all of these three junks, seems to have the best result for these three types of PDEs. But of course, we wanted to try it. We're still working on trying it on different types of PDEs and also with higher dimensions. This is just a little parenthesis just to say that a similar method also that uses Laplace approximation has been already applied also to other types of neural operators. In this case, in particular, if it was graph neural operators. And in this case, it was applied to the Darcy flow. It was just a little parenthesis to refer to another work that we've done 2 years ago. What you can see, this is the error of the difference between the prediction of a Darcy flow and the actual ground truth. On the left, you see the error. So this is just the difference between the prediction and the ground truth. And on the right, you see the standard deviation. So to compute the left plot, you actually need to have the ground truth. And on the right plot, you don't. This is actually the uncertainty estimate. So you try to quantify the error. So you don't have the ground truth to compute this. And we were happy to see that it actually is able to quite precisely spot the errors with the biggest error that you can see in red and on the corner. Here I omitted some details. What were the input and outputs? The inputs were different lambda functions, and the output will be the U, so the solution for that lambda. Okay, let's conclude. What did we do? So we tried first to provide FNOs with uncertainty estimates using Laplace approximations. And we did this in a very basic way by using Laplace approximation to find the posterior distribution over the weights. And this brought us to different ensemble predictions. Then we tried to generalize this question and ask, okay, what can we do to put a Gaussian belief over an operator? So can we give a probabilistic reinterpretation of FNOs? And we did this through the framework of GPs with functional programming, so carrying, and using linearized Laplace. So actually the two of what we needed compared to 0.1 was linearization, so having a linearization of the network and the framework of Gaussian processes. And we ended up with what Nola, which is a Bayesian version of FNOs. Thank you. I hope I didn't go too fast. I'm sorry, I was a bit nervous because I misunderstood the time.
Don't worry about it. I think it was great. Are there any questions also from online or inside the room? If not, I have views actually. So can you put the slide again, Emilia? So
yes.
Some reference as well. So I wanted to ask first of all, regarding the first method,
Yes.
you show some results for long and short training. We're referring extrapolation in time. Is it correct?
Yeah, sorry, I didn't mention that. This is just that short training we just stopped earlier. So we stopped the RMSE when it reaches a certain threshold. For the short training, I think it was 0.28, and for the long term, it was something like 0.09.
Okay, my question was related on have you experienced some problems in how the, let's say, uncertainty propagates through different times for the PDE? So, you know, you tested Burgers, KDV, so those are dependent PDEs, and like I expect that, let's say, the uncertainty bands change as the times evolve. So
Yes. In fact, so we tried, so these were trained on 20 time steps, and then we looked at the prediction of the next, I think it was 10 or a next bunch of time steps. What we tried, for example, we tried to plot how the uncertainty evolves in time, and we saw that the uncertainty increases in time. This is actually what we expected to see, or we wanted to see, that by using this Laplace approximation, the uncertainty, like the average uncertainty, let's say over this is one function. So we took the uncertainty over the whole function and plotted it as a single number in time, and this went up. So this was actually unexpected behavior, or not expected, but a good behavior for this uncertainty quantification method, because it means that the more far away in time you want to predict, the more uncertain you want to be, or not you want to be, you expect to be, because you know, like it's more difficult to predict in 10 time steps with respect to 1. So this is something we tried to take into account, and actually it was good that the uncertainty went up, or the standard deviation. Was this the question that you asked?
Yeah, well, it was actually like this, and also did you use an autoregressive kind of way of applying FNO, or you augmented also in time the other dimension? Like what?
I didn't understand the question. So you mean if we? So in this case, it was the training input was just a batch of time steps, and then it was a prediction in, let's say, the next 20 time steps. Okay. So the initial, sorry, the input were the initial conditions. Maybe I didn't mention this.
Yeah. Okay. I have another question as well, and maybe I will leave other people asking questions. Do you? I mean, when you do your approximation, is something I didn't get. Is it the covariance metric? Is it diagonal, or does it have also correlation? Because losing correlation in weights, I think it's a big lose when you do one such.
Yes, this is a fair question. So we try to. So there is always a trade-off between, since there are the number of parameters, so R can be actually very high, even for a 4-layer Fourier neural operator. This can be a big matrix, the one that we compute for Laplace. So what we did, it was a k-fac approximation, which is still better than a diagonal, because the diagonal is really only on the diagonal, whereas a k-fac is a block diagonal approximation. So it takes a bit more into account, but still, yes, you have zeros outside of this, which is mainly due to computational cost. So I see your point. Ideally, you would like to have the whole matrix, definitely. But if the network is small, you can do that. Otherwise, you have to be careful, because it can take forever. But yeah, I definitely see the point.
Yeah. Okay. Are there some questions also from online? If you have any question, you can unmute and just ask the question. I think we will. Okay, so maybe Anna, we want to say something.
Let's thank again Emilia for.
Thank you very much. Thank you very much for inviting me.
And yes, see you all at the next AJS.
Okay, thank you very much.
Thank you.
Thank you.
Ciao, bye.